Okay, so for 9.4 and 9.5, we're just going to do, well, I'll do all of 9.4, but then just the first half of 9.5. So we're going to be working with our polar coordinates and polar graphs. And so there's a few ideas that we need to just review from your trig days. So our first review idea here is that cosine theta is equal to our x over r. We also use it where we have x isolated as well. So if I multiply the r to the other side, then I would get x is equal to r cosine theta. And then sine theta is y over r, and our isolation for y, so multiply the r over, we would get y equals r sine of theta. And this is actually the format we'll use the most in terms of our calculus concepts where we apply them. And then tangent theta is equal to y over x. And then our last relationship is the Pythagorean relationship. So where when you multiply, or excuse me, square the legs of a triangle in Adam, it's equal to the hypotenuse squared as well. Okay, so let's go ahead and take a look at how we're going to convert. So again, this is a review idea that might come into play occasionally, but it's really just how do we, work with those formulas, and how do we work with converting back and forth between polar and rectangular in case like maybe we have a struggle with graphing. So our first step is we always want to replace our trig function, because we want to make sure that anything in terms of theta and r go away. So rectangular form, let me see what that is. So that's when we get like y is equal to a function of x. And it's not always a function. So if that's the case, then it'd just be in terms of x and y's only. So our first step is to replace whatever trig function we have in terms of x, y, and r. So for this particular problem, we have sine of theta. So we're going to replace sine of theta with y divided by r. So that'll be our first step. So I still have a r, and then sine theta will substitute for y over r. And then our next step is we want to clear fractions. So for this particular problem, we don't want to have that divide by r. So then I'm going to multiply both sides by r, and it will cancel on this side. And then I'll have r times r, so r squared, and then is equal to y. And then we're still not in terms of y as a function of x yet, or in terms of x's and y's only. So we have one more step, and so that will be to substitute or replace any remaining r's. So at this point, we shouldn't have any thetas or trig functions because we did that in step one. And so now we have an r squared. So we're going to use this replacement here. So we'll use our Pythagorean theorem relationship. So instead of r squared, we're going to replace it with x squared plus y squared is equal to y. And then we're not going to get y as a function of x because I have that y squared and x squared. So if I were to graph this, this would end up being a circle, but I would have to do some completing the square to get it into that format. Okay, so how do I know it's a circle? Because I have a sum of the squareds with equal coefficient. Okay, so that is just, a little review there. So again, this is the piece that we'll use the most, and we'll see that in the next step in terms of like how do we apply this to kind of calculus ideas. So just like we had on the previous lesson with our parametric equations, that whenever we wanted to find the derivative of y with respect to x, when we're given parametric equations. So we have parametric equations here. So we have x as a function of theta instead of t, but it's still our independent variable. And then y as a function of theta as well on this one here. And so we have parametric equations. So that derivative, and instead of with respect to t, it'll be with respect to theta. So I have the derivative of y that I will have to take in terms of theta, and then the derivative of x in terms of theta as well. And so if I look at the numerator here, this is just the product rule. of y equals r sine theta. And that is, again, just derived from sine theta is y over r. And then our denominator, again, is just the product rule as well, but in terms of our x component, which is x is equal to r cosine theta, right? So if that's equation 1 times 2. So this would be, 1 d2, and then plus, here's our 2, and then our d1. And then the same for the denominator. So it looks, complicated. Like you look at this and you're like, oh man, geez, that's like super complicated. But it really is not. It's just product rule. So it's a good review off of our chapter 2 days. So we're using our x is equal to r cosine theta, our y equals r sine theta, and then we're just applying product rule to find dy d theta over dx d theta. Okay, so not the worst thing in the world. All right, so let's go ahead and take a look at an example here. So it's asking us to find the slope of the curve at theta equals pi over 4. So in order for us to be able to do that, we have to at least know what our slope is first, right? So we're going to have to find dy dx. And then we know from up above, like x is equal to r cosine theta. So this is our r equation that we have right here. And so we're going to apply that to the x and the y formulas as well. Okay, so let's run the steps down. So in order for us to find dy dx, we need equations of y and equations of x. So that's going to be our first step. So we're going to create our two equations. So we'll find x is equal to r cosine theta, and then we're also going to find y is equal to r sine theta. So, and then our r is going to be substituted for whatever the given r function is, which in this case is 2 minus 2 sine theta. So I'm actually going to find my y first, just because I know that I want to find dy over dx. So I'm going to write the y first, hoping that will keep me in the numerator correctly. So y is equal to r times sine theta, but our r equation is 2 minus 2 sine theta, and then so that's this part, and then still times sine theta. And then now I'm going to do the same for x. So x is r cosine of theta. R is still, hasn't changed, 2 minus 2 sine theta. So that's that portion, and then times cosine theta. And then once I have my two equations, then I'm just going to do product rule. And I'm going to do product rule for both the x and the y. So product rule for y and x. And we're going to have that be as a quotient, right? So we're doing our dy d theta over dx d theta. Okay, so I know this is going to be quite large, so I'm going to run this off to the side over here. So dy over dx. Okay, so this is going to be my equation 1 and then times equation 2. So I'm going to do product rule. So I have 1 d2, so 1, and then d2, so the derivative of sine is positive cosine, and now plus equation 2, and then d1. So then I want to take the derivative of this. So the derivative of 2 is just 0. And then the derivative of negative 2 sine theta would just be negative 2 cosine theta. And then that's 1d2 plus 2d1. I'm going to do the same thing for my x. So now this is going to be my equation 1 and then equation 2. So equation 1 hasn't changed. It's just the 2 is now cosine. Okay, so for dx d theta, so I'm going to do 1d2. So 1. And then d2, so the derivative of cosine is negative sine. I'm just going to move that negative to the front. So there's 1d2, and then plus equation 2, and then d1, so that will still be the same. Okay. All right, and then I could certainly simplify this a little bit if I wanted to, like I don't need the 0 minus 2. But I do know that I need to evaluate it. So since I have to evaluate it, I'm going to go ahead and just substitute and simplify at that same time. Okay. So there is my dy dx. So then now to find the actual slope, I'm now going to substitute my value of theta in. So substitute theta. And then in this case, it'll be with pi over 4. And then at the same time, I'm going to go ahead and simplify just a little bit. So anywhere I see a theta, I'm going to replace it with pi over 4. And you can also evaluate at the same time. For sake of notes, I'm not going to. So I would have 2 minus 2, and then sine of pi over 4, and then times the cosine of pi over 4. And then I'm going to go ahead and simplify this at the same time that I do my substitution. So 0 minus 2 is negative 2, so I'm going to do negative, and then 2, pull that to the front, and then sine of pi over 4, and then cosine of pi over 4. So I essentially just, got rid of the 0 and then just moved the negative 2 to the front. And then for the denominator, I would have negative and then parentheses 2 minus 2, and then the sine of pi over 4, and then times the sine of pi over 4. And then the same thing here, so that minus 2, I'm going to pull to the front, and then I would have cosine of pi over 4, and then times itself. And then evaluate, so you can't leave it as like the sine of pi over 4, you actually have to evaluate it, and then we'll end up with a complex fraction, so we'll have to simplify that as well. So I do know that both sine of pi over 4 and the cosine, so sine of pi over 4 and the cosine of pi over 4, they're equal to each other because that's at that 45-degree mark, and that's just root 2 over 2. So everywhere I see a sine or a cosine of pi over 4, I'm going to replace that with root 2 over 2. Okay, so then, oops, sorry, I got distracted with my phone buzzing. Okay, so sine of pi over 4 is root 2 over 2. Cosine is also root 2 over 2. And then I'm going to do the same for the bottom. So I have that negative out front. And then 2 minus 2, and then root 2 over 2. And then sine of pi over 4, root 2 over 2. And then all the way down. So lots of substitution right here, lots of root 2's over 2's. And then I'm going to go ahead and simplify. So I know, for example, let's see, like that will cancel here. I'll cancel a pair of 2's there, a pair of 2's here, and here. So I'm going to go ahead and write what I have just so I don't lose track of stuff. So that first grouping is 2 minus root 2. And then I still have a root 2 over 2. And then I'm going to multiply these together. So root 2 times itself is square root of 4, which is just 2. So that would be just 2, and then still divided by 2, so that would just be a 1. And then in the denominator, I have that negative out front. So 2 minus radical 2, and then times radical 2 over 2. And then over here, I'm going to have minus, and then that would be square root of 4, which is just 2 over 2, which is just 1. Okay, so let's see here. So I have to get rid of the over root 2 or over 2, so I don't have that complex fraction. So I have a couple choices here to make that happen. I'm probably just going to take that easy route and just multiply the numerator and the denominator by 2 just to clear that fraction and then call it good. And of course, you can distribute and combine like terms. I'm just going to go ahead and distribute in that 2 to simplify the complex fraction component and not go any further than that. So I would still have 2 minus the square root of 2, and then now times root 2, because the 2's would divide, and then 2 times 1. And then over here, I'm going to distribute this 2 as well. So I still have that negative. And then the root 2 over 2 would cancel the 2's, and then negative 1 times 2 would be negative 2. And then, of course, I could distribute, could combine like terms, simplify further, but I'm going to call that good because I'm out of my complex fraction form, and we'll say there's the end of that. Okay, so now we're going to take a look at our 9.2 So 9.5, we're going to be looking at area and arc length, but for just this first half, we're just going to look at the first half of 9.5, and we're going to focus on area of our petal graphs. And we'll do a tiny bit of a review, not a giant one, of how do we graph petals. So our area formula for polar coordinates is definitely different than our area formula of just our functions. So the area formula that we're going to be working with is 1/2. So there's always this 1/2 in front. And then we'll have radial lines of alpha and beta. And then we take our function squared. Okay, so it's definitely very different than our normal area, right? So our area that we did with Riemann's, right, our rectangle area was from A to B of f of x dx. And the reason it's different is because in function form, this is summing up areas of rectangles, right? Because we have like that base times height, and that's how that was created. And that's because that's how we plot our points, right? So if I want to plot a point, I go over so much and up so much. And so I'm finding the area of that, right? Over so much, up so much, I'm finding the area of that. And so this is giving me like, you know, my dx, remember, is just like the shrinking base. And then my f of x is the height. And so I'm finding the areas of all of these pieces here. And then the integration piece is adding them up from A to B. And so polar coordinates don't graph the same way, right? We don't go over and up. So that's not how we graph our polar. And so that is why this formula is different, is because I'm not adding up areas of rectangles, I'm adding up areas of sectors of circles. So let's like maybe get a visual of that. So when we plot points for polar, is we always rotate to a radial line, right? So here, let's rotate to alpha since we have alpha for a lower limit. And then we go out whatever that distance is on that radius. So then from the pole, we would go, say, like to right here. So whatever that R value is. And then we're going to rotate to the next radial line. So we'll call that beta. And then when we rotate to that, and we go out however far we go. And so if I want to find the area, so what I'm looking at is I need to figure out what this area is here, which is different, right? So we're not going to the x-axis creating rectangles. We're going and we're creating like these little sections here that are sections of a circle, right? So we look at a sector of a circle, and that's where that formula comes from. So if we just start with just what is the area of a whole circle, so that's pi r squared. If I want to know the area of a sector of a circle, so I'm going to use S for sector, I know the total area is pi r squared, but I want to know just how much of that part of the circle out of 2 pi. So a full rotation, right? If I do a full rotation, that's 2 pi, but I'm just trying to figure out what is a partial rotation, so whatever the angle is over 2 pi. So the pi's would reduce, and then I would end up with 1/2 r squared theta, and that's where these formulas come from. So there's the 1/2, there's the r squared, and then instead of just theta, it's d theta, because again, we're shrinking that distance down so it's negligible, so we get an accurate area. The beauty of calculus, working in small things. Okay. All right, so there is our formula that we're going to be working with. Okay, so let's redo a couple reviews of how do we graph polar equations. So just kind of as a quick little reminder, we have in general, like our function is r is equal to a sine or cosine b theta, where a is the length of the petal, and then 2b is the number of petals from 0 to 2 pi. But the trick here, so this is going back to the good old days. So if b was odd, the petals overlap. And then if B is even, then you have distinct petals, meaning that they won't overlap. So if we look at here, so this is 3 theta, right? So then there really are 6 petals, but 3 are on top of 3. So we would only see 3 petals, okay? So we would draw out only 3 petals. Because the other 3 petals would just be exactly in the same location. They would be on top of each other. So 3 petals on top of 3. So, because 3 is odd, right? So here we have 2 theta. So that means we would have 4 petals because 2 is even. So then we would draw out all 4 petals. Okay. All right. So, and then each petal length. So this first one, they would be 4 long, and then this one would be 3 long. So lots of different ways to kind of attack this problem, but typically, like I would just plot a couple of points from the quadrantals. So I would find theta and r. So I'm going to just do a couple of quadrantals. So I'm going to replace theta with 0. So I would have 4 times cosine of 3 times 0. So 4 times cosine of 0. And then also as a little reminder, so at 0, this ordered pair is 1, 0, and cosine is the x value. So then that would be 4 times 1, so that would be 4. So my polar graph is different than my xy. So I'm going to draw it as an xy, but remember that your polar graph paper is concentric circles. So there would be like, you know, a bunch of like concentric circles that would be radial lines that come out. But I'm going to skip that portion because that's like a lot of extra drawing that's going to happen. So I'm going to rotate first. So I go to theta equals 0. So that would just be right here. And then I'm going to go out 4 units. 1, 2, 3, 4. So there's that dot. And then I'm going to do another one. So let's do pi over 2. So then this would be 4 cosine of 3 pi over 2. And so 3 pi over 2 is down here. That ordered pair is over 0, -1. So cosine of 0 would be 0. 4 times 0 would be 0. So I would rotate to the pi over 2, and then from the pole go nowhere, so there it would be there. So that gives me my first petal, so then I'm just going to kind of draw that first petal in. And so I know that I have to draw in 3 petals, and they have to be equally spaced. So since I already have 1 petal, I'm not going to keep plugging in points because I can figure out where the other 2 petals will be. Okay, so I have to have 3 petals between 0 and 2 pi. So that means I have to do a total of 2 pi, right, is 1 full rotation, and I need to squeeze 3 petals in, so divide by 3. So that means that the next petal is going to be 2 pi over 3 away from the 0. So that would land it right around here, right? So that's where 2 pi over 3 is. And then I would go out 4 units, and that would give me my second petal. And then I would go another 2 pi over 3, which would put me at 4 pi over 3. So definitely not very to scale. And then 4 units out. And that would give me my next petal. Okay, so pretend there's symmetry and beauty there. All right. Okay, so let's go ahead and do the next one. So 3 sine 2 theta. So I'll be looking for 4 distinct petals because B is even. So the odds overlap. And so instead of seeing 6 petals, I see only 3 because the other 3 would be overlapping. All right, so again, I always start out with just doing a t-table and then substitute in a couple quadrantals to kind of get the gist of where my petals are going to land. So I'm going to put in 0. So that would be 3 times the sine of 2 times 0, which would be 0. So I'm going to refer back to here, sine being my y value. So 0 times 3 would just be 0. So my first point is at the pole, so 0, 0. And then now I'm going to go ahead and substitute in pi over 2. So I'll get 3 times the sine of 2 times pi over 2. So that would be pi. So pi is over here. Y value is also 0. So 3 times 0 is 0. So that's not helpful. All right, and then let's go ahead and substitute in pi and see what we get. So then we would get 3 times the sine of 2 pi which, hey, that's 0. So if you see a trend, then stop, right? Because like, that's not going to be very helpful. Okay, so then that is not good. So then I'm going to try something else. So let's try pi over 4. So let's see what happens at pi over 4, right? Because plotting 0, 0 4 times is not going to be helpful. So then I'm going to just put in another special right triangle value. I'm going to just do pi over 4. So then I would get 3 times the sine of 2 pi over 4. And so that would be the sine of pi over 2. So pi over 2, so that's up here, and that ordered pair is 0, 1. So that would be 3 times 1, which would be 3. So at pi over 4, so that's like smack dab in the middle here, I'm going to go out 3 units, and then that gives me my first petal. And then as soon as I get 1 petal, I don't need to keep plotting points because I can then use my knowledge of equally spaced petals. So I have to squeeze in 4 petals between 0 and 2 pi. So I'm going to do 2 pi divided by 4, which is pi over 2. So that means that this petal is at pi over 4. So then I want to go pi over 2 units over here to find my next one. So let's get a common denominator here. So pi over 2. So I'm going to multiply by 2 over 2. So that would be 2 pi over 4. So then my next petal is going to be at 3 pi over 4. And then out 3 units. And again, that's because there's the 3. And then I'm going to go another 2 pi over 4. So that will put me at 5 pi over 4. Out 3 units. Man, these graphs are horrifying. Okay. And then another 2 pi over 4. So that would be at 7 pi over 4. And again, pretend there is beauty and symmetry in my polar graph. Okay, so that's just a quick review on graphing. And you do need to make sure that you know how to do a little bit of the polar graphing by hand, because that will show up in a no calculator portion occasionally. All right, so let's put the practice into calculus. So what do we need to do? So we're going to be looking for area. So in order to do that, we're going to go ahead and graph. So the 3 cosine 3 theta, so we already graphed cosine of 3 theta, so we have an idea of what the graph is going to look like. The only difference is instead of going out 4 units, we're going to go out 3. So we already have the idea of the graph. So let's go ahead and just mimic that. And I only need to do it for 1 petal, so I'm only going to draw that one in. So I'm going to just go out 3 units though, instead of 4. And then I have this graph. And I know there's 2 more petals, but I only have to find the area of 1. So then our job now is to figure out, well, how do I find the area of that? So the area formula is 1/2, and then the integral from alpha to beta of r squared d theta. And so that's just from above. So we have our r. So the hardest part of this whole thing is trying to find our alpha and beta. So our alpha and beta is the lines that kind of sandwich the graph. Let me try to draw that a little better. Okay, so what we're looking at is, where is alpha and beta in terms of that will create that picture. So this will be my alpha and this will be my beta, right? Because I want to be in between these two. So alpha needs to be smaller than beta. So if otherwise, like I'm going to be, coming around the circle on the outside. So what I need to do is figure out when does that graph enter and exit the pole, right? So that's what I need to do. So I need to figure out when is the radius equal to 0, because that is where the graph enters and exits the pole. That's where alpha and beta will reside, okay? So I just need to solve for when 3 cosine 3 theta is equal to 0. And that's when it will, the petal will begin and end when the radius is 0. So I'm going to divide both sides by 3. And so now I need to know, when does cosine equal 0? So cosine is equal, and I only need to really find one of them because then I'm going to use symmetry. So cosine is equal to 0 when the x is 0, right? So over here, the ordered pair is 1, 0. Up here, 0, 1. So cosine is 0 when x is 0, so that would be at pi over 2. And then finish solving, so then I'm going to multiply by 1/3, so then theta would equal pi over 6. So that would be what my beta is. Beta is pi over 6. So my alpha, due to symmetry, is just going to be negative pi over 6. So then my area would be 1/2, and then negative pi over 6 to positive pi over 6 of r squared, and then d theta. And that would give me my area. So words of caution here. So this is, just some mistakes that I see students will make, is that they will say, well, this is also considered 11 pi over 6. Okay, so if we try to say, well, then can my integral be from 11 pi over 6 to pi over 6? Like, could it be that? Well, but that's not what we're doing, right? So are we going from 11 pi over 6 to pi over 6 to do that graph? So keep in mind that that's saying the same thing as the integral from negative pi over 6 to 11 pi over 6, right? If we flip it and put the smaller angle on the bottom. And so that's really this section over here, right? So that's really going between on the back side of it, which is not drawing in this petal, which is the one that we're trying to draw in. Okay, so we always want to make sure that we understand that for polar, we have to go in that counterclockwise direction for a positive direction. So counterclockwise meaning I need to start here and end here. So starting here, then I need to go from the smaller value, which would be negative pi over 6, to the larger value, which is positive pi over 6. All right, and then let's go ahead and take a look at, like how would I type in, something like that in order to, in either my graphing calculator or in Desmos. And so I'm just going to show it in Desmos. So let's go ahead and do that. So let me jump into my Desmos screen. Okay, so INT will get us that integral. And I forgot the 1/2 out front. Not 1.2, but how about 1/2? And then for my upper limit, it was pi, so I'm using the letters pi, and then divided by 6. And then my lower limit is negative, and then pi divided by 6, right? So negative pi over 6 to pi over 6. And then quantity, so it was 3 cosine of 3, and then theta, so type out the words theta. And then my squared is all the way on the outside, and then d theta. Okay. And then you should make sure you're in radians. So I'm just going to check my settings. I should be. And so right here it says radians. So then my value would be 2.356. Okay, so let's run into here. And so then I know that my area, so this area here would be, what was it, 2.356, I believe? Yeah. Okay, so let's go ahead and do one more. So for this one here, so we have r equals 4 sine 2 theta. So again, I'm going to use the same graph. So 4 sine 2 theta, the only difference will be I'm going to go out to 4 units. And then I only need to graph one, so I don't need to graph all of them. So 4 sine 2 theta. So that graph would be over here, out 4 units. And so now I'm trying to figure out, when will I go through the pole, right? Enter and exit the pole. So then that's when r is equal to 0. So my first step is to set r equal to 0 and then solve for that. So I'm going to divide both sides by 4. And then when does sine equal 0? So sine is my y value. So if I look at this ordered pair, that would be at 0. So 2 theta would be equal to 0, and then divide by 2, so theta would be 0. So then that would be right here, right? So when is that graph? So that graph is between 0. And so I hope like we can see then also between 0 and pi over 2. So that petal is sandwiched between 0 and pi over 2. So what I want to find, so my alpha then would be 0, and then my beta would be pi over 2. So that area would equal 1/2, and then the integral from 0 to pi over 2, and then r squared. And then I'll let you guys do that. And that is the end of this lesson.